pass to the nature of matter, the history. At the end of the 19th century, matter and energy were distinct, were different. So the matter was thought to consist of particles, whereas energy in the form of light. And when we talk about light, we talk about electromagnetic radiation that is characterized by a wavelength and the frequency. So it was described as a wave. So that means at the end of the 19th century, they make difference between matter and energy. And in the next slides, we will see that we have, for example, for light, we have two forms, which is particles, and at the same time, which is the form of energy. Particles were characterized by a mass and position in space. So when we talk about person, for example, we can determine his mass, and we can determine his position. So now I talk about history. The wave were described as massless, no mass, and delocalized, so no position. That is, their position in space could not be specified. It's also assumed that there was no participation between matter and light. So as a conclusion, as history of the matter and the energy, at the beginning of the 19th century, we make difference between matter and energy, yani no relation between matter and energy. The matter is characterized by particle, and the particle has mass and position. The energy is characterized by a wave that has no mass and delocalized, so we cannot know the position. After this time, they discovered that we have relation between the matter and the energy. So Max Planck did an experiment. He heated a piece of iron till 727 degrees Celsius or till 1000 Kelvin. The unit of conversion of temperature is Kelvin or degree Celsius, and 1 degree, we add 273, we obtain the temperature in Kelvin. So degree Kelvin equal degree Celsius plus 273. I return to the experiment. Max Planck heated a piece of iron. He observed that the light starts red. With time, we continue to heat. The color of the metallic piece become yellow, and if we continue the heating, the color turn to white. So the color turn from red to orange. At temperature greater than 2000 Kelvin, the light is still brighter and white. So he asked the question, why we have difference of light on the metallic piece? So Planck conclusions. He said that the energy absorbed by the iron piece is directly proportional to the frequency of the light emitted. When he started the heating, the color was red. He continued the heating, the color was orange. And at the end, the color was white. لما بحكي أنا, when I talk about colors, so I see these radiations. And these radiations are emitted due to the heating of the metallic piece. So the first conclusion of Planck, the energy absorbed is directly proportional to the frequency of the light emitted. The second conclusion, the matter can absorb or emit any quantity of energy, so the energy is quantized. What is the meaning of energy quantized? You know that we have several colors. We see only by Planck experiment 3 colors, the red, the orange, and the white. We did not see other colors. So the radiations are specific, and any radiation is characterized by energy, we will see later. So the energy can take a determined values, so the energy is quantized. Meaning the term quantized means it could not take any value. So the value of this energy is well known. Also, he concluded that the energy can be gained or lost in a multiple of quantity called quanta. And he calculated the energy released is equal to N H nu. What is N? N is integer number 1, 2, 3, 4, 5, etc. Mu is the frequency of the radiation absorbed or emitted, and H is a constant. So Planck concluded that the energy of the light emitted is directly proportional to the frequency of this light. So the energy of light emitted or of the radiation emitted is equal to a constant times the frequency of the radiation emitted. These are the Planck conclusions.